Welcome back to CS 712. In this session, I'm going to talk about context-free languages. You guys have been working with context-free languages throughout the semester, so you already know what they are, but let me just back up and restate the definition. Context-free languages are generated by context-free grammars. So context-free grammars have productions of the form a single non-terminal goes to a string of terminals and non-terminals. And the string might be empty, so this could be an empty rule. This could be lambda on the right-hand side. Okay, and again, you can imagine more powerful, more complicated grammars where you have multiple symbols on the right-hand side being rewritten to symbols on a string of symbols on the left-hand side being rewritten as a string of symbols on the right-hand side. But context-free means we only have a single non-terminal on the left-hand side, and we're going to rewrite it independent of any symbols that might be around it during the derivation. So that's what they mean by context-free. Okay. Now, when we look at regular languages, we discovered a language that is not regular. Right? We're using a Pumple lemma. We showed that a to the n, b to the n is not regular. But it's easy to show it's context-free because it's generated by this grammar. S goes to lambda and S goes to ASB, and we can draw some derivations down here to show how the language is generated. So the case where n is 0 is just one application of S goes to lambda. To get A, B, it's just one application of the second rule followed by an application of the first rule. And obviously I can generate longer strings in the language by just applying the second rule as many times as I want. So here's 2 applications to get 2 A's and 2 B's, or 3 applications to get 3 A's and 3 B's. Okay, and always at the end we use the empty rule to get rid of the start symbol and stop the derivation. Okay, so again, a derivation starts with a start symbol. We use the grammar rules as rewrite rules, and we rewrite the into a string of terminal symbols. And one term I'll use is that one of these intermediate steps is called a sentential form. Okay. When we think about that A to the n, B to the n is context-free, that means that the set of regular languages is a proper subset of the set of context-free languages. So every regular language is context-free because it can be generated by a regular grammar. A regular grammar is context-free grammar, so every regular language is context-free. But the reverse is not the case, right? We just saw a language that's context-free and not regular. Therefore, the set of regular languages is a proper subset of the set of context-free languages. Okay, what about recognizing context-free languages? Well, the mechanism that's used to do that is called a push-down automaton. So it's basically a finite state machine with a stack grafted onto it. The stack is initialized to contain a single symbol. The stack has the usual push and pop operations, but also we can choose not to operate on the stack if we want, the no-op or the no operation. Okay. The arcs of the finite state machine now are labeled with both an input symbol and a stack symbol. So to take this arc to go from state I to state J, we would need L to be the next thing in the input, S to be the top of the stack, and we could also then operate on the stack. So let me just read this, make sure I got that right. If the PDA is in state I, and either L is next in the input, or L is lambda, meaning we don't care about the input, and the symbol on top of the stack is S, then we execute the operation and we move to state J. And if L is not equal to lambda, then we advance the input, right? We've matched that input symbol. So you think about it, a finite state machine simply just had the arcs labeled with L, right? We transitioned in the finite state machine the DFAs by just matching something next in the input. Okay, we'll call these instructions. We'll summarize this as an instruction. Again, I have the I and the J as members of this tuple. I have L, which we're hoping to match in the input, or it's lambda. We have the top of the stack that we need to match, and then we have an operation. And in fact, I'm going to allow a sequence of operations in that position, just as a convenience. Okay. Now what determines, what specifies that a string is accepted by the PDA? Well, I'm going to require that we empty the stack and that we consume all the input. And there's no particular requirement that the PDA be in any particular state. So with DFAs, we had the notion of final and non-final states, and we expected to consume the input and end up in a final state. Here, though, I'm just going to consume the input and empty the stack. As you read textbooks and so forth, you may see other formulations of this termination condition, but this is the one I'm going to use. Stack is empty and the input is consumed. Okay, what about determinism and non-determinism? Well, the PDA can be non-deterministic if there's more than one move possible from a particular state. How does non-determinism show up? Well, it could be two arcs labeled with the same input and stack symbols. So again, I have the same condition on the input and the same condition on the stack, but I'm either going to a different state or I'm doing a different operation on the stack. So having a choice like that, that's what we mean by non-determinism. Or I can have the kind of non-determinism I had in an MFA, where I have two arcs labeled with the same stack symbol, or I have one arc is labeled with lambda and the other one with an input symbol. In other words, I have multiple ways to go. Okay, so that's non-determinism. Well, here's the theorem that says that the language generated by any context-free grammar can be accepted by a PDA. And a proof is another one of these constructive proofs. You give me a CFG, and I'll construct the PDA to recognize the language generated by the CFG. An interesting thing here, I don't need multiple states. I can get away with a single state. So I can initialize a stack. There's 4 steps to the construction. The first step is I initialize a stack to contain the start symbol. And basically, we're using the stack to keep track of our parsing goals. Initially, my goal is to match the start symbol. Right? I want to prove that the input is an instance of what's derivable from the start symbol. Okay? So that's how I initialize the stack. And then for every terminal symbol A, I create the instruction. Again, my I and my J, my state I'm in and the state I'm going to is always going to be the same here because there's only a single state. Everything's going to be 0, 0. But for each terminal symbol, when I see A next in the input, I really should say it the other way. When I see A on top of the stack, I expect to match it against A in the input. And so I'll consume that A and I'll pop it off top of the stack. Okay, so again, when my parsing goal is a terminal symbol, I expect to just match it against the input at that point. Okay. Third case is for every production that has a non-empty right-hand side. What do I do then? Well, the instruction is I don't care what's in the input, but if big A, the left-hand side, is on top of the stack, I'm going to pop it, and I'm going to push the right-hand side in reverse order onto the stack. Okay, and why do I push it onto the reverse order? Well, again, the rationale here is that my current parsing goal is A. That's what's on top of the stack. How am I going to match an A? Well, to match an A, I need to match a B1, a B2, up to Bn. And I need to match B1 next, so I need to push B1 last, so it becomes the top of stack after I'm done with this instruction. Okay. Finally, the fourth alternative is when I have an empty rule, so A goes to lambda. Before I say that, though, let me just back up because my notation here may be a little misleading. I've drawn these with capital letters, implying perhaps to you that they're non-terminals, but in fact, the right-hand side can be a mix of non-terminals and terminal symbols. Okay, and when a terminal symbol rises to the top of the stack, it's going to be matched against the input. Okay, when a non-terminal is on top of the stack, then we're going to process its productions. All right, back to the empty rule. When I see the empty rule, I'm going to create an instruction. It just says I don't care what's in the input. When I see the left-hand side on top of the stack, I'm just going to pop it. So basically I'm saying, well, I'm satisfying the goal for A. I'm considering it matched because there's an empty rule available to me to do that. Okay. All right. So why does this work? Well, the PDA accepts the language because each state transition with a non-terminal on top of the stack corresponds to one derivation step. Let me go back to this slide. Right, when I take A off the top of the stack and replace it by that, that's exactly like a derivation step, or rewriting A to be the right-hand side. So basically, the PDA is just doing a derivation. And so it's just mimicking what the grammar does to generate a string, and that's how the PDA can accept the string. Notice that the non-determinism might be used to make this choice. If I have multiple productions for a given non-terminal, basically the non-determinism allows me to try all the choices. Okay. All right. So again, the PDA accepts the language because it's basically doing the derivation. Let's look at an example. Here's again the grammar for A to the n, B to the n, and here's the PDA that we constructed from that. Again, the terminal symbols would just be matched, right? When I have a terminal symbol A on top of the stack, I expect to see little a next to the input, and I just pop the stack. Same thing for B. And I have another rule for every production. So here's the empty rule. Don't care what's next in the input, but when I see S on top of the stack, I just pop it. So I replace S with nothing. Or I replace S with its right-hand side, ASB. I end up with A on top of the stack, S underneath it, and B. So I push them in reverse order. And of course I pop the S off first. So let's watch a derivation here. If I have 3 A's and 3 B's, that's clearly in the language. I initialize my stack to have S. And that's really the initialization of the derivation, right? I start with the start symbol. And right off the bat, what happens? Well, I've got an A on top of the stack, but an S on top of the stack, A next to the input, S on top of the stack. So I have a choice to make. The non-determinism allows me to sort of go both directions at once. But what happens if I choose the null rule? If I replace this S to nothing, I empty my stack, and I'm stuck because all my instructions require there to be something on top of the stack to proceed. So choosing that rule in this case would be a dead end. So in my display here, I'm only showing the steps that actually lead to a successful parse. So in fact, what I want to do here is I want to choose this instruction. I want to replace that S with ASB. Okay, and that corresponds directly to a derivation step. Okay, and now I have an A on top of the stack, and I have an A next to the input, so I'm going to match those off, consume both of them, right? End up with just 2 A's now in the input, and I have S on top of the stack. And again, I'm back to this S on top of the stack. I have to choose one of these. If I choose this one again, I get rid of this S, and I have a B on top of the stack and a little A next in the input, and those don't match, so I'll get stuck. There's no instruction to allow me to make progress from there. So again, that would be a dead end. So what I want to do, in fact, is use this rule again and replace that S with ASB. Again, that's another derivation step where that S got replaced by this ASB in the middle here. Okay. That leaves me with an A on top of the stack. The A gets matched against that A gets consumed. This A gets popped. Returns me to an S back on top of the stack. Again, I have this choice to make. If I choose this one, again, it would end up with a B on top of the stack and an A next in the input. That's not going to work, so I've got to use this one again. So I rewrite that S to be ASB. Again, that's a derivation step. S being rewritten to be this ASB. It leaves an A on top of the stack. A can be matched against that A and consumed. So we end up with 3 B's in the input and an S on top of the stack. Finally, this is the case where I want to use the null rule. If I don't, if I use this rule, that will end up with an A on top of the stack, a B next in the input, and that will make me get stuck again. So in this case, this one's wrong. Now I want to rewrite the S to be nothing. All right, so I just pop the S, and that's the final step in the derivation of replacing that S with nothing. Okay. PDA is actually going to have to wind down and empty its stack before it can declare success. But now it's got 3 B's on the input, 3 B's on top of the stack, so there's just going to be 3 traversals of that self loop to match the B's off and empty my input and empty my stack. And at that point, the PDA will declare success. Okay. So that's how the PDA works, and that's how you can see that it's doing a derivation as it goes. Now, it turns out in that particular language, A to the n, B to the n, I could do it deterministically. Let's look at this PDA, which is deterministic. Again, it has the same matching of the terminal symbols. Those two instructions are the same, but now these are slightly modified. And basically, I'm using one symbol look ahead now to decide what to do. If I have an A next in the input, I am going to use the second rule in the grammar. If I have a B next in the input, I'm going to use the first rule. That's essentially what's going on here. So it's one symbol look ahead. Let's do a quick trace using this input, AA, BB. So I start out with a start symbol on top of the stack and S next in the input. S on top of the stack and A next in the input. So that's this case, right? So I'm going to pop the S, and this time I'm just going to push B and S. In essence, I'm matching the A implicitly here, right? Rather than pushing the A like I did in the last example and then matching it in the next step, I just say, you know what? I know it's going to match. There's no reason to push it. So I consume it off the front. Okay, that leaves me again with an A and an S. So it's going to be another use of this rule. Pop that S, replace it by SB, consume the A. Now I've got B's on top of the stack, right? Sorry, I've got B's next in the input, S on top of the stack. So that's an occurrence now of the empty rule, of the instruction that corresponds to the empty rule. So in this case, I'm going to consume off the S, pop off the S, and then I'm going to pop of a B because I'm matching it against that B. Again, I'm not going to bother with pushing that B essentially and then matching it in the next step. I'm just going to match it directly and just do a pop. So I pop S and B, consume that B off the input. Now I just have a B in the input and a B on top of the stack, and that's just a final traversal of that loop to empty the input and empty the stack. So sometimes you can manipulate the PDA, come up with an equivalent PDA that's deterministic to match the language. But in general, it turns out you can't get rid of the non-determinism. Unlike with finite state machines with DFAs and NFAs, the PDA needs non-determinism in some cases to recognize context-free languages. Okay, so in general, we're not going to be able to get rid of the non-determinism. Also, at this point, I just wanted to point out that the parse is really top-down. If you think about this, right? I start with a start symbol, and I derive. I guess I should go back to this other slide, which has the derivation written out. Let's go back to the other example. All right, it's really top-down. I start with the S, and I work myself rewriting things to end up with a string of terminal symbols. So it's top-down in the sense that I'm drawing the parse tree from the start symbol down to the leaves, which are the terminal symbols. Okay, so it's top-down parsing. Also, it's not obvious from these examples because there's only one non-terminal, but it's doing a leftmost derivation. Leftmost derivation means that at each step in the derivation, I choose the leftmost non-terminal in the current sentential form. Again, this example is too simple, but I'm always operating on this S. There's only one S. But if you could imagine a right-hand side of a grammar rule that had two non-terminals, when I push it on, the leftmost one is going to be topmost, so it's going to be matched next, and that's what we mean by doing a leftmost derivation. Okay, so again, leftmost derivation means rewriting the leftmost non-terminal in the sentential form, where sentential form is an intermediate step in a derivation. Okay. All right, let's talk a little bit more about non-determinism. As I said a moment ago, non-determinism is sometimes necessary, and the prototypical example is consider the set of even palindromes over some alphabet. In this case, I've said the alphabet is A, B, so it's a string W followed by the reverse of that string W. That's the legal strings in the language. And I can write a context-free grammar for that pretty easily, just 3 productions. But it turns out the PDA cannot be rewritten without non-determinism. And here's a somewhat convoluted PDA for that to recognize that language, but it's just illustrating at some point I jump from a state where I'm sort of in the front half to where I'm in the back half, right? Because the way it would work is I need to push the string I see, the W here, onto the stack. It would be, and I could match it off in its reverse order, right? If I push the front of W first, that means the back of W will be available to me to match up, and I can match it off. So that's why the PDA will work. The problem is, how do I know where the dividing line is between W and WR? And the non-determinism, it has to be used here. So I jump from sort of recognizing the front half to recognizing the back half and matching it off against the stack. There's always going to be some lambda transitions to do that. There's no way to get rid of that. And this has implications for parsing real languages, basically. We can't get rid of the non-determinism, and that gives us problems when we're implementing compilers for real languages. And we'll talk about that later in the course. One other thing I should say at this point, I'm not going to do the proof, but you might ask if PDAs, we just showed that PDAs will recognize all context-free grammars, but do they do more? Is it possible that a PDA could do something that was more complicated than context-free languages? And the answer turns out to be no, that it's a complicated sort of proof, but you can show that given a PDA, you can generate from that a context-free grammar that will generate the same language that is recognized by the PDA. So in fact, PDA recognizes exactly the set of context-free languages. All right. Well, one last slide. This is where we're heading. So we move from the theoretical to the more practical parsing algorithms. The first one we're going to look at is called LL1 parsing. It does a leftmost derivation. The LL, again, the rightmost L is leftmost derivation. The leftmost L is read input left to right. I guess in the old days, people thought maybe would be any reason to think about reading the strings in reverse order. But it turns out that nowadays all the parsing algorithms are left to right. So LL1 parsing is what you would do by hand if you were stuck on a desert island without a parser generator. You'd probably sit down and come up with a LL1 parser. You'd write it by hand. It would be top down. You'd start with the start symbol and start trying to derive the input from it. And if you think about it, LL1, the 1 here indicates we want to be able to choose the right production with just one simple look ahead. So the big question is going to be, I'm on top of the stack. I have a non-terminal on top of the stack. I want to replace it with one of its right-hand sides, and I want to be able to do that with one simple look ahead. But this is restricted. I just said a moment ago that we can't do things without, in general, we can't parse context-free languages without using non-determinism. So certainly one simple look ahead is not going to be adequate either. So in fact, LL1 parsers only parse a subset of the context-free languages. But the nice thing about them is the parser can be generated with a table. It can be implemented with a table essentially. If we have this table, I call it the select table. It's two-dimensional. It's indexed by a non-terminal, that would be the non-terminal on top of the stack, and the current input symbol. And then we can always tell what the right-hand side we should use for big A. All right, we're in this, we see big A with little a next in the input, big A on top of the stack, little a next in the input, and I'm going to replace big A on the stack with the right-hand side of the production, of a particular production of A. And if I could always make that choice based upon just the one symbol lookahead, then that language is called LO1, but that's not going to always work for context-free languages. It's not all the context-free languages, but it turns out to be a big enough set that it's been used to parse many real programming languages. And that's where we're going to head next, is looking into, how can we, a parser generator really, for an LO1 parser, generates this table automatically. It reads the grammar and generates this table. Then you just plug this table into a generic parser that manipulates a parse stack similar to the way the PDA manipulates it, but now it's deterministic, right? We've restricted the grammars we're willing to process so that we can always make the choice based upon the next thing in the input. And so, the next topic is to try to, what are the algorithms that would allow us to do that would allow us to read the grammar and generate that table. All right, let's stop here.